I don't know. Then they go inside of some other thing that only God knows, and other stupidity happens.
Oh, no. I meant the actual image rendering of a black hole.
Yeah. Okay. No Marg, no Maggie, no Megan.
I don't know when Megan.
Ken's here, Cody's here, Alina's here, Lauren Lee's here, Safish is here, no Tioni, Sarah's here, Eliezer was first here or second here, Labor, Holly, Dylan, and Caleb. Okay, so the three people I don't see are Maggie, Megan, and Tioni. Okay, just to re-say what I said earlier, it wasn't until this morning that I discovered that the homework that I posted was not visible to you. So it's visible to you now. I'm sorry that it wasn't until this morning. This morning, like around noon, that it became visible to you. Is that going to be a problem to anyone? Has anybody had? Eliezer, we know that you had no idea. So, yeah, the homework.
For Wednesday?
Yeah. Is that not a problem? I mean, I want to make sure if somebody says that's a problem. I planned on doing it Sunday and it wasn't there.
Is it as long as it was last week?
It's 6 questions.
Okay, that shouldn't be a problem.
Okay.
Hopefully it's not as long as last week. Yeah, you can do it.
Okay. Today we're going to talk about geology of the earth. What's the first thing that comes to your mind when I say today we're going to talk about geology of the earth?
I think the mountains.
About the history of the life of Earth.
None of you guys are like me because the first step that comes to my mind is seriously? Astronomy class for studying geology? And actually I guess it's the next slide after this. But yeah, there's a good reason why we study some small amount of geology in astronomy. We're going to be studying in this section the planets. And we're making measurements of things on planets. Most recently made measurements of the dwarf planet Pluto. And then we compare them to what we know from Earth to try to interpret them. So everything we're going to be looking at today about the geology of Earth is specific to things that we see and observe and interpret on other planets. Now, this one here is just a review slide, the 4 steps in planet formation. Differentiation, I actually have that coming up in a slide, but differentiation is when you have materials separate by density. So more dense things sink, less dense things float. We talked about that last class period. Flooding can be both water flooding and magma flooding, where you have liquid on the surface of the planet that floods out and makes a nice smooth surface. Then you have cratering. Cratering impacts with things, debris, asteroids, planetesimals in the early stages, leaves lots of big pockmarks. We see lots of pockmarks on things like the moon and Mercury that have had very little of the last stage. The last stage, the one I didn't talk about, slow surface evolution. That is the slow change. You need to brush more than that if you want them to be clean. Your lesson for today, when you brush your teeth, you're supposed, I always first go like this to try to clean them a little. But then you're supposed to put the bristles at a 45-degree angle and just sit there and go like this to drive the bristles between the gums and the teeth so that they will disrupt stuff in there and get anything out of there so you don't get pockets of infection. That's the way it's supposed to work. Just so you know. Yes, on with astronomy. The slow surface evolution is very visible on Earth because we have a lot of atmosphere and water on the surface that causes weathering and erosion. Weathering is breaking this material apart. Erosion is moving it. On the moon, one of the things they found is that you have a very thick dust. There's been a lot of weathering, very little erosion. That is, you've had a lot of micro impacts that have broken up the surface to make that dust, little erosion to move it. So those are the 4 stages of planet formation. All planets have had a certain amount, but things like Mercury have had very little of this last one. Okay, so here's my slide on really studying geology. Why? Yes. Because we need to know it so we can compare things we see on planets to what we see here to try to understand it better. So what have we studied of the solar system? First of all, we have visited the Earth.
No duh.
Yeah, no duh, exactly. We've also landed on the moon, 6 times. We have not sent humans to any other objects besides the moon and the earth. And it didn't take a lot of work to get to the earth. All you had to do was fall out of bed. We have landed...
Quite a big deal.
We have landed spacecraft on a number of other objects. Venus, look, 4 failed missions to Venus, 10 successful, 1 partially. The longest lander on Venus was there for 110 minutes.
Before it melted.
Yeah, because Venus has a caustic environment. It's hot, it's chemically unpleasant, so things don't last very long there in Venus. Mars, you can see Mars now. I don't think we've sent anything up to Mars in the last year, but I didn't update these numbers since I looked them all up last year. 49 missions, 21 successful. That's not a good success rate. There are some people who proposed that maybe there was an intelligence that was trying to keep us from exploring Mars, and that's why they had these failures. One of the most dramatic of all failures, I think this was a Mars failure, was when there were people working together in a team, some in the US and some in Great Britain, and somebody gave a parameter in British unit or English units, the ones that we use here in America, and somebody thought that it was in metric units, and so it crashed because they had the wrong numbers. You know, that kind of mistakes. Really sad when you've put millions of dollars into something and it was the wrong units that messed you up. On a test, that could be 1 point on a test, but here it's millions of dollars.
Did they found any water, frozen water on Mars?
That was the announcement from, what was it, a week or so ago, that they have actually found flowing water or liquid water on Mars. It was kind of a Hollywood stunt as well. It was timed to go with the Martian movie premiere, which seemed odd to me. And I haven't gone through and looked at it carefully. They've been spending so much money on this. I already talked about Dan Quayle back when he was vice president. Yeah. I was in graduate school then. That was before I started my teaching career. So it's been a long time in coming. So 21 successful missions, 7 still operational. We've got those rovers up there, you know, Spirit, Opportunity. Can't remember any other ones. But there's plenty of missions there. Jupiter has had atmospheric probe, that is something that comes down and goes through the atmosphere and makes measurements of what gases are present and sends them back.
Doesn't the probe get crushed?
Yeah. It's a one-way trip. They
don't come back.
We have sent spacecraft to land on a couple asteroids and even a comet. So we've done a lot of exploration. And of course, I didn't show things here like, you know, we had flybys of Mercury not landing on Mercury, flybys of Pluto not landing on Pluto. So there's a lot of exploration that's been done. We don't send humans out there because
It might not come back.
not just might not. Unless you were going to Mars, you wouldn't come back. So it's not a great thing. So first clicker question, and I have to advance it before you can answer. This is going back to the Flip Friday of a week ago, actually. What are the most common elements in the Earth's crust? The top 2. And notice it is important that we note that this says crust. When I was preparing, I found that I had the answers to all clicker questions wrong last year. I think I wasn't worried about what the answer was last year. I've gotten more sophisticated. Okay, Holly. There we go. All right, we had 2, 5, 2, 4. Well, we don't have a clear answer here. The correct answer, and we'll see in a slide that's coming up in just a moment, the list, or you could just look right here. Alina has her book open.
No, I didn't know.
And we see that oxygen makes up 45% of the crust and silicon 27% of the crust. And then what's third? According to this, it's aluminum. According to what I had found elsewhere, it's iron. So,
Yeah, I read somewhere it was iron.
yeah. So apparently there are different people putting out different numbers. I'm not the master, but those are the most common. What do you know that's made of silicon and oxygen? What? Okay, yes. I wasn't sure what you had said, and I didn't want to say something. You say, well, that's not what I said. Yes, silicates. Silicates such as quartz, glass. Diamond is not a silicate. Diamond is carbon. Most people know that sand is silicate. Most of our rocks are actually silicate rocks. So that's a big portion of what we have around us, is silicon and oxygen. I'm sorry to hear that. So here's a beautiful picture of Earth. I hope and pray that we can identify what part of Earth this is. I say this, and I'm going to go through the exercise because there are people who might think this is America.
It's not?
Ha ha ha, very funny. Okay, this is Africa. So what's this island right there?
Madagascar. Hawaii. Greenland.
Cuba and Greenland. Okay, you guys are funny. I got to give you that.
There's Saudi Arabia, there's India.
Okay.
Also Iran.
So here we have the Arabian Peninsula with, Saudi Arabia is a big portion of that. And Egypt over here, and country where my brother and sister were born is right over there.
Why is it brown?
Why is it brown? Okay, this is modified color because you also see what color are the oceans? Brown. They're trying to show us what the actual structure, surface of the earth is without vegetation. And so they've tried to use the color that you would have for the actual surface if you take away the vegetation, if you take away the water and so on.
We would look like Mars.
Yeah, pretty much. We would look a lot like Mars. What gives Mars its red color?
The iron and the oxygen.
The iron and the oxygen forming what we like to call rust. So Mars is rusty, that's why it's that color.
So is it not because of its core elements or?
Well, it's the crust. You only see the crust.
Right, but I mean, is there something like at the core that's turning things into more iron as they go towards the surface?
No, in fact, as we understand the transmutation of elements only occurs either in the death of a star where you generate all kinds of elements or in nuclear interactions, in nuclear decays of some kind. And it turns out that iron is the ultimate stopping point for nuclear decays. That is, it's the most stable of the nuclei. Everything else could either add something and move toward iron and become more stable, or something bigger, break into smaller pieces and move toward iron and become more smaller. That's not even right. But that's a very trace thing, and it's not like you don't have a machine that can grind it out. Okay, so, and we understand that this is Africa, so we have South Africa down here and whatnot. So our surface, we said silicon and oxygen combined to form silicates. Average density of the Earth is 5.5 grams per centimeter cube. But the crust is only 2.8 grams per centimeter cube. So we're walking around here in the crust of the Earth, and we tend to think, you pick up a rock and that thing's pretty dense. Well, if you look at it, it's about half of the average density of the Earth. So in a relative sense, it's not very dense. And of course, you look at water, water's less dense than that rock. We're basically the same density as water. Fairly low densities, actually. the density of your body or of water is similar to the average density of a Jovian planet. This time I made it so the clicker question is available first, although I think there's, yeah. Which is not a reason for the density of Earth's crust to be lower than the average density of the planet. Remember I said the crust was about 2.8?
I think that you worded this question wrong, or we just said okay after one aspect.
Oh, yeah, I changed it. You're right. I changed it back, changed it again. So yeah, I think you have to put in an answer and hit enter because I made it so it's multiple. Yeah, but there's only one right answer.
Okay, because as soon as I saw that, I figured, okay, the original question must have looked more like, which
Well,
is the reason.
It actually started with this wording. Then I changed the wording, changed the answers, changed the wording back.
So in essence, this question is actually asking which is a reason.
No, it's saying which is not. Two of them are correct, one is incorrect. And you're supposed to identify the incorrect one.
So we're supposed to find the correct.
You're supposed to find the correct one. Or you're supposed to find the incorrect one. Two of them are correct. One is not. You're finding the one that is not. Okay. 1, 3, 10. Now this one here was probably, well, it was designed more to be educationally than previous knowledge. The moon is not part of the Earth's average density. Furthermore, the moon is less dense than the Earth is. So there were two problems with that one. You wouldn't have known the second part. Gravity does compress the Earth, and gravity is going to cause things that are in the center to be compressed more, kind of like if you are laying on top of your bed, sure, you're being compressed by the atmosphere, but that's not much. If you're lying on top of your bed and your 5 best friends decide to pile on top of you, you're going to be compressed more because of the weight above you. And that's what's going on with the Earth. The stuff in the center is compressed much more because of the weight of stuff above it. And so the Earth has a compressed density. In fact, they calculate, I mentioned this earlier, the uncompressed density for the Earth is somewhere around 3.5 grams per centimeter cubed. That is, if there was no gravity compressing the Earth, that's what the average would be. And lower density materials float, so the lowest density of all the materials on Earth should be the stuff we find at the surface. So there's another reason why the crust should be less dense than the average density for the planet. Okay, so here is a breakdown that I found, or actually this is fairly similar to what we have in the textbook, right? 8% aluminum, 6% iron. I forgot where it was that I found those switched. If you look by the number of atoms instead of the mass of the atoms, you get a slightly different picture. Now, who can tell me why those two are not the same if you're comparing the mass versus comparing the number of atoms?
Because each atom has a different mass.
Each atom has a different mass. So, for instance, something like iron that has a fair amount of mass to it, iron has a mass that's, what, about twice the mass of oxygen or something like that. Okay, if I get closer, I can actually read. Iron's mass is about 56. Oxygen is 16. So if you were to take those numbers and compare them, 16 to 56, that's more than a factor of 3. So the one iron atom is more than 3 times the mass of one oxygen atom. So that means when you're talking about mass, the iron is going to have a higher percentage. When you're talking about the number of elements, it's going to have a lower percentage when you compare it to oxygen. And so you can look up there and see iron goes from 6% of the overall mass to just 2%, so it dropped by a factor of 3. oxygen, 46% of the mass went up to 60% of the number of elements. So you can see why there's a difference there. Why am I pointing this out and even showing both numbers? Because you'll see some comparisons by mass and some comparisons by the number of atoms, and it's important to understand what they mean and that you can translate from one to another, but know what the point is, how you can have those numbers. Okay, how do we know anything about what's going on inside the Earth? Surprisingly, or maybe not, we have not been able to dig very deep into the Earth. The deepest that has been dug into the Earth is something in the ballpark of 5 to 7 kilometers. Now that's a big distance if you're digging with a shovel. They're, of course, digging with things like well drilling. But what happens is they get deep enough and it gets very hot, so it starts making their metal soft. And it starts to get kind of flowing just a little, so it oozes. And so it just kind of grabs their bits and breaks them off. And so they've had a very hard time trying to dig. So how are we going to know anything about what's inside the Earth if we can't dig there?
Yes.
Okay, you guess. That's not a terrible answer. What'd you say?
Right.
You said, well, let's do what's up there. Earthquake waves. Now there are other things. Things like studying the Earth's gravitational field also tells us about what's going on inside. Okay, but earthquake waves is a very primary way of understanding what's going on in the Earth. There are two fundamental types of earthquake waves, and I can illustrate those waves with my handy-dandy slinky.
Yes.
So, here, Labor, help me out. Hold one end of my slinky. Just hold one end. Okay. So the two kinds of waves you can make are first a wave that goes like this. I pull it up so it's closer to me and let go. See the wave that went back and forth? That wave was what we would call a pressure wave because we have places where it was pulled together, we call those compressions, and places where it was spread extra far apart, we call those rarefactions. So when I let this go, you had that pulse of compressed wave that traveled down. Now with the P wave, you know that the velocity, the direction that the wave travels, was parallel to the distance or to the direction that the pieces of the slinky moved. Now the other kind of wave, so Labor just did. The other kind of wave, if I lift up and let go, then we have a pulse that is in the vertical direction while the wave is traveling horizontally. That's called an S wave. S stands for either shear or secondary. P stands for either pressure or primary. Those words both have meanings. Primary means the first one. Secondary means the second one. Yeah, I know. That's shocking to all. That's because the primary wave is faster. So when you have an earthquake, the first wave you get is the primary one because it's faster. The second one you get is the secondary because it's slower. But then there's also the pressure to tell us that's what we call in technical terms a longitudinal wave. Longitudinal waves, the motion of the ground is the same direction that the wave is traveling. The S is for shear. A shear is when the motion is perpendicular to the direction of travel. So
you might, so like if you were, depending on where you were from the source of the earthquake, you might feel like the ground shift before you see like cracks.
Well, yeah, depending on where you are in an earth, how many people have felt earthquakes? Okay, we at least have some. I mean, from the age of 5 till, majority, I lived in California, we had plenty of earthquakes. Different earthquakes feel different. It depends on where you are with respect to the focus. By the way, you guys have heard the word epicenter, right? A lot of people think that means where the earthquake happens. What epicenter means is the point on the surface of the earth above where the earthquake happens. And so the focus or hypocenter is actually the name for where the earthquake happens. If you're directly above that, you're probably just going to have an up and down motion. If you're off to the side, then you'll have the first thing that comes will be making you go like this, and then the second thing will be making you, and so the motion changes. And depending on where you are, you're going to have different kinds of motions. Another really important thing about these waves, the P waves or pressure waves can go through anything except for nothing. The waves cannot go through a vacuum. The S waves can only go through solids. So if you have a liquid, you won't have an S wave. If you have a solid, you can have both the S and the P waves. That's an important piece of information because when you have an earthquake, you have all the detectors on Earth set up to find where you see the waves. And in this picture, you can see if you're over here, you'll get the nice P wave. The P wave is this thing that's coming out. And then you get the S wave. So you have both the S and P wave. But if you're over here on the opposite side of the Earth, you don't get the S wave. And so this picture is reconstructed based on that information. Based on the information of where you get the S wave and where you do not get the S wave, scientists have calculated that there's a liquid core in the Earth that causes a shadow region for the S waves. And the size of that liquid core is determined simply by how big the shadow is. Inside of that liquid core, there is a solid core that's not labeled here. By the way, if you play WoW, that liquid core is the molten core, okay? No, the S wave only travels through solid. A P wave travels through both liquid and solid. So how do we know there's a solid core inside of that liquid core? Well, the P wave can travel through the fluid. When it hits the surface of the solid, it will cause S waves to go around that solid core. And then those S waves will cause waves to radiate outward from the boundaries of the solid core. And so by looking at more detailed information than you see here, they can determine that there's also a solid core inside of that liquid core. So in the end, the Earth has 4 pieces that will be laid out in the upcoming slides. But for now, you have the crust, which is the thin layer on top that's black on this side, blue everywhere else. So the crust is the uppermost layer. Then you have the mantle. And the mantle is the biggest portion there that's red. It's hot, very uniform actually, material. Then you go down far enough in the mantle, you get the liquid core, which they believe to be probably molten iron and nickel. You might ask, why iron and nickel? How did they come up with that? They came up with it based on calculations of what elements should be common on the Earth, which ones are going to be most dense of the common elements, and by differentiation, they expect those things would have sunk to the center. And then inside of that, the solid core. Yeah. Slide 11 of 28. We are moving right along. All right. I have 2 questions here, so this one you should, if I set it up correctly, you should enter 2 correct answers and then hit enter. I say if I set it up correctly because this morning was a technological nightmare. Given that I have no answers yet, I assume that that's the way it has to work. And yes, Sarah, you proved me right. Uh-oh.
What?
That's going to disappear in a moment.
So it's multiple choices?
It's 2 correct answers and then hit enter.
Did you run out of battery?
No. Remember I told you this morning was catastrophic. Even this failed this morning. It was everything that failed. Yeah, well, I had a warning. It told me that it had quit before it stopped showing it up there. Okay. We had 10, 0, 3, 3, 8, 2.
So does this mean that primary waves can pass through gas as well?
Yes.
Okay.
Yes.
Can they pass through plasma?
Plasma is just ionized gas, I guess.
Yeah.
Yeah, when we get to the sun, I'll talk about some people get all stinky. No, it's a plasma, not a gas. But a plasma is a gas. So. Okay, so when we look at this, 10 people said P waves travel faster than S waves. That's correct. And what was your key to remembering that? Primary. It gets there first, hence it must be faster. 8 people said P waves can travel through liquid. That's also correct. I don't have some nifty way of remembering that. I mean, if we get into the details, we can talk about it a little, but we're not going to get into the details in this class. So those are 2 things that are important to us for understanding what's going on inside of the earth. So now let's look more carefully at the layers in the earth. So the outermost layer is the crust, which ranges from 20 to 70 kilometers in depth. Now you might wonder, why is there a difference in depth? You have 2 fundamental types of crust, the ocean crust and the continental crust. The continental crust is less dense, and it grows thicker to get to the same mass that the ocean crust. The ocean crust is more dense, it's thinner. And so that's why we have a range. The thinnest ocean crust is about 7 to 10 kilometers thick. That's where people have tried to drill through the crust to see what the mantle's like. The mantle, it's hot but not quite molten rock. It actually is subdivided. If you take the mantle and the crust, the mantle we break into 2 pieces, the upper mantle and the lower mantle. And in between them, we have the asthenosphere, which is considered in geology terms like the grease on which the lithosphere moves. So what's the lithosphere then? The lithosphere is this here.
The stone sphere.
Yes. So the lithosphere is the part that moves on top of the asthenosphere and includes part of the upper mantle. So that's where we start. We have the crust that's only about 20 to 70 kilometers thick. Then we have the mantle, and if you look over here, you can see the extent of the mantle. It goes from about 3,500 kilometers up to 6,357 if you get to the edges of the crust. So if you subtract those 2 and then take away about 30 or so, you have what, 1,800 kilometers thick for the mantle. And then inside of that we have the molten core and finally the solid core. So those are the things that we believe the earth is made up of. Why do we believe it? What's our evidence? Why is it not just a guess? Earthquakes, looking at the seismic waves. Now, there's another piece of evidence as to why there's a molten core and why it's made out of something like iron, because we have a magnetic field. Our understanding of how magnetic fields are created is to create a planet-wide magnetic field, you have to have melted material that conducts electricity, that is swirling around in a circle, and has convection. Convection we'll see in just one more slide. So the fact that we have a magnetic field tells us we must have something like that going on in the core. It's called the geodynamo. Oh, not the next slide, after this. This is just talking about temperatures and pressures. When the Earth initially formed, it would have been hot because of all the stuff falling inward. You get hit by planetesimals, you have gravity crushing things, it makes it hot. Also, radioactive decay would have caused the Earth temperature to get hot. we believe that the core of the Earth is still about 6,500 kelvins. That's a little bit hotter than the surface of the sun. The surface of the sun, the photosphere of the sun, is about 5,800 kelvins. So we're talking about 700 kelvins hotter at the core of the Earth than the surface of the sun. That's, I think, a little impressive.
You know why?
Well, the original formation caused a lot of heat. In fact, they call it the heat of formation, right? The heat of the planet forming and gravity compressing things and things falling in, that caused a lot of thermal energy. And then the Earth is pretty big. I mean, sun big? No. But pretty big, compared to you and me, yes. And so because it's big, the surface area of a sphere is proportional to the radius squared. But the volume is proportional to the radius cubed. So the rate at which it loses energy compared to its total energy is proportional to 1 over the radius. So the bigger an object is, the more slowly it loses its thermal energy as a proportion to its total. So very large things cool very slowly. Small things will cool very rapidly. Hence the illustration up there of having a little piece of your entree on your fork. It will cool quickly. Whereas you have an entree sitting on your plate with a big chunk of it, it cools much more slowly. It's because of the surface area to volume ratio. And that covers what I had on that. You see surface area to volume ratio, see that right there? Yeah. Okay, here's where we talk about the convection. Convection is one of 3 mechanisms for heat. Heat is the transfer of thermal energy. Mechanism number 1 is real simple, conduction. If I touch this, I can have heat flow. If that is hotter than I am, heat will flow into me and I will feel hot because of the energy coming in. If that's cold in me, heat will flow out of me. I'll feel cold because of the energy leaving. So that's conduction. The second mechanism is convection, which is a transport of energy through an intermediary. In the case shown here of a soup, I presume, you have things like peas and carrots in there, in the water. It's heated at the bottom. At the bottom, then, you're going to form things like bubbles that float up to the top. And you have energy, thermal energy, transported through the material like that. In the sun, convection is an important mechanism as well. Convection makes hot material in the sun float up to the surface. Hot materials, by definition, hot means they're moving faster. They move faster, they're going to collide with things more and push them farther away, so they spread out, become less dense, and then they float up. That's the reason for convection. What does it have to do with the Earth? The Earth has convection going on in the mantle. That is, you have heating from that hot core that causes convection. Wow, red was not the color to use. Didn't notice what color I was in. White will be a great color here. Causes material to cycle. Of course, what's going to happen with this hot material here? It's going to come up. And so some places you have hot material come up through the crust, making volcanoes, right? So the Hawaiian Islands are a hot spot, a place where you have the convection coming up, pushing up, and making volcanoes. All of the Hawaiian Island chain is technically one volcano because it's one hot spot. But as the crust slides over, it punches through in different places. So each island represents how the crust has moved over that hot spot. So how does that convection affect us? Well, for one thing, it gives us oceans. So here we have a picture showing how it gives us oceans. You have these mid-oceanic ridges where convection currents are causing material to come up and push up through the crust. And so it's much like I envision Samson from my books that we had, the little bedtime stories we had as kids. Some places say that he put his arms around the pillars and pushed them in, but I always saw the picture of him pushing out. And that's what's going on here. that hot magma, the yellow in the picture, is coming up and it's pushing the ocean floor apart. And so the ocean floor is slowly spreading. You can see in that picture at about 2 centimeters per year. Now that's a little impressive when you think about it, especially, I used to live there, Monterey Bay Academy. We've got the ocean right there. And to know that this is coming in at me 2 centimeters a year, you start to understand why we're having earthquakes. So you have the ocean floor being pushed out by hot magma coming up. Now that magma is just molten rock. So when that melted rock meets water, what clearly happens?
Igneous rocks.
Well, yes, they are igneous, but it freezes and forms basalt. Is that what you said?
I said cool.
Okay. So it freezes and forms basalt. And so you have the ocean floor. Basalt is just a term for relatively quickly frozen rock. If it freezes super quick, then it's obsidian. It's glassy. If it freezes really, really slowly, it'll be granitic. It'll have big crystals in it that you can see.
Like granite.
Yeah, granitic. Granite, yes. So the ocean floor, it freezes relatively quickly, making it basalt. It's pretty dense, and you're constantly laying out new ocean floor. And then you have the ocean is traveling over here, and the ocean floor is, and when that ocean floor gets to a continental mass, you have two things hitting each other. Well, something's got to give. And generally what happens is the more dense one sinks underneath the less dense one. We call that subduction. So the more dense piece will subduct underneath the continental mass, which is less dense. But then you have the grinding of one plate against another. Grinding, as you know, you just take your hands, go like this, and it gets warm. Well, that kind of grinding generates a lot of heat, so it melts rock. Melted rock becomes less dense. That less dense rock floats up, and it creates volcanoes. So you can map out where the edges of the plates are by looking for the volcanoes. Where you have that subduction, it causes volcanoes. What else does it cause? Earthquakes. Earthquakes because you are creating stress by having all of that sliding. That stress then makes fractures in the earth break apart, and that's an earthquake. So, looking at plate boundaries, I say just look for the volcanoes. Here's a map from the U.S. Geological Survey, USGS, that shows where you have lots of action. And you see all those little red dots and the words Ring of Fire. I'm from the coast, so I grew up in the Ring of Fire. And yes, and it burns, burns, burns. That Ring of Fire. Yeah. Now, something that I like to point out to people, especially because, we had movies like San Andreas. I grew up right on the San Andreas Fault, right? Monterey Bay Academy, the road in front of the academy is called San Andreas Road. Why? Yeah. So the San Andreas Fault comes in and goes inland here. Now, technically, anything to the west of the San Andreas Fault is on the Pacific Plate, an ocean plate. So if you look at that, technically, the coast of California, most of it is in the ocean. When people say the big one's going to hit and California's going to fall into the ocean, it already is, yeah. And nothing super spectacular is going to happen in terms of going underwater. What is likely to happen, now if you notice in this picture, well, it doesn't show you, but you have motion going like this because of those rifts, the ridges in the center of the ocean. So you tend to have subduction, but we are currently, instead of having subduction, we have what we call a strike slip. The ocean plate tends to be going like that against the continental plate. So when the big one happens, you might have a couple meters of slippage, which if you're talking your house and one half of your house slips 2 meters north of the other half, That's kind of catastrophic. But in a global sense, 2 meters doesn't seem that big. That's what would happen. And there are places like, if you go to, what is it, Parkview, California, something like that, it's somewhere in the Visalia area, you find houses that have their sidewalks that are like sheared and offset like that because they're sitting on top of a fault. Question, Caleb?
Yeah, what about that one in the Antarctic plate that's not next to any fault line?
You're talking about this here?
Yeah, the one bottom.
You said what?
Yeah, the one at the bottom.
Oh, you said Antarctic, yeah.
Yeah, Antarctic.
So, I can't really say. I'm not well enough versed. Sorry. I can say that, this Nazca plate is a real mover. So the biggest problems in the world are Chile as far as earthquakes because that plate moves a lot. And you guys know about the earthquake there in Haiti. I went to Haiti right after the earthquake, We're going to wait for it. The damage there was pretty extensive. There was an earthquake that was like 300 times more energy in Chile like a week later. Nobody even talked about it. Why?
Chile was built for it.
That's right. Chile was built for the earthquakes. So their buildings can withstand it. Haiti was not. And so Haiti had, large destruction. It's the building code. So California, earthquake country, they build for earthquakes, and it's not that dangerous. In fact, it's more dangerous out here with tornadoes. Natural disaster danger is bigger here in the Midwest than it is in California.
We only have typhoons every, most years, but we're built for 700 mile per hour winds.
Yeah, but what was it, 15 years ago or something like that, you guys had something pretty devastating.
Well, we had something sort of devastating that the typhoon talked about, and that was because we still had some old houses that weren't built up.
So you cleaned up the trash? Is that what you're saying?
Basically.
Okay.
Probably somewhat.
Plate boundaries. We've already talked about that. This picture here is really important to understanding something about how we understand the plates. It wasn't until the 1900s when the idea of these moving plates was even introduced, which is surprising. I mean, when I was a kid, obviously when I was a kid it had been introduced, let's not get confused. I looked in the maps in the World Book Encyclopedia. My brothers and sisters and I just read the encyclopedias. That's what we had to do. We didn't have to. That's what we did for fun because it's what we could do. Anyway, and you look at the maps, you're like, wow, South America and Africa totally fit together. And so you're like, maybe they used to, maybe there's something there. That's essentially what the idea of plate tectonics is. That you can see this here and this here, very similar in shape. Maybe those used to be together. It was initially scoffed at, of course, just like all good ideas. But then when people learned about these mid-ocean rifts and the rifting action that's pushing them apart, they started realizing that really makes sense. And so now we believe that really, truly, these used to be together. In fact, I know I'm out of time, but I'm going to stop with a video showing a recreation of what we believe. Well, yeah, what science has put together for the history of the globe.
This is very expedient. It was made a lot faster and all.
Right.
Isn't there a theory that there was once more earth and water before the flood?
I could talk about that, but for now I just want to look at this because we're out of time, and then we can talk about it later. If you look at the time here, we're talking 2.2 billion years ago right now. There's a pretty big uncertainty on the times. This comes from looking at magnetic fields stored in the rock in the ocean floors.
The planet was formed from hot and fire, then where did all the water came from?
The scientific theory is that it came from comets.
The Bible says that the water was there quite a while before God created any life on it. So this is still quite plausible.
Where do the comics get their water?
Got
They're made of ice.
Now, if you look there, the green is what is now North America. And down here where it says Channel 33, unfortunately, is showing us the names of the supercontinents. So right now we have Columbia is the name given to this big thing. That is 1.5 billion years ago, according to theory. Now you look at that and you don't see anything that looks like today's world, right? Doesn't look like the globe. I was saying, I hope you'd recognize that's not America on the globe. Well, if you look here, you wouldn't recognize that green thing is North America.
yellow is Antarctica and Australia.
So are those light blue patches just pieces of Earth that will later disappear?
To the best of my understanding, if you look right there below where it says polling closed, the colors tell us that light blue should be Eurasia.
Oh,
Oh, he's talking about like the white.
Yeah, the white I'm guessing is unresolved landmass. Yeah. Now we're into the supercontinent of, I think it's Rodinia. Those have been changed. I haven't noted every one.
That poor little mass is just floating away. No! Oh, whoa! It's moving so fast. No, it's on.
Whoa.
hey, look, Hawaii.
When
Yeah.
when you get to the end and you see India come flying up, that's my favorite part.
Oh yeah.
India is just like a bat out of heck.
Yeah, I never understood that whole part. But
So now we're on to, it's not Pangaea, I don't know what it is. Now we have Gondwana. Then we'll go to Laurasia and Gondwana in a few.
Dang it! I just want to see something, recognizable now.
Well, we're getting close.
Yeah,
After we get to Pangaea, then you'll start recognizing things.
Why is it moving so fast all of a sudden?
Because it's passing
Good
forward.
question.
It was
So
like-
here we're in Pangaea,
What is the white supposed to be? The
and now
Arctic?
you'll start recognizing continents.
What is the white supposed to be? The Arctic?
See Africa.
Yeah, you see Africa, South America.
Yeah,
North America.
I see it.
And North America is still not very well defined as far as
Wow,
the
Europe
shape.
used to be a lot bigger.
Yeah.
Russia.
This here is India.
It's Eurasia.
That's India.
What?
Happened to that?
Going for the final.
Cue the Himalayas.
Oh, I guess that makes sense.
Ta-da.
So
Oh.
at the rate we're going, we're not going to have a Mediterranean Sea for long.
Anyway, I find that very interesting to look at, and that is not
Yeah.
just whimsy. That is built by looking at magnetic fields frozen into rocks in the ocean floors.
Megan, you have not let an email.
Yeah, I did.
Send me about.
I'm sorry, I was on the mountain. I didn't get it until today. I need to go to class. I'll talk to you later.
The other one is.